So this week we are going to begin our unit about climate change. So we've been looking at different kinds of natural hazard events that can affect us, and climate change is the big one. Climate change is a process that is dramatically reshaping our Earth, something that is going to be part of our reality for the rest of all of our lives. And it's something that feeds into a lot of different sorts of hazards that we're going to have to deal with. So we're going to spend several weeks talking about climate change, how it works, what its effects are. And since the climate is a state of our atmosphere, we got to start by understanding what the atmosphere is. So in this lesson, we're going to try to understand the composition and structure of the atmosphere of the Earth, and to be able to explain some of how human activity has changed the atmosphere. So here's a diagram of the composition of our atmosphere. So the atmosphere is a thin envelope of gas that surrounds the Earth. So the outermost layer of the Earth above our crust is made out of gas, and it is the atmosphere. And the atmosphere comes in several different layers. And it's important to remember that with a gas, you can compress it to a much greater density, or it can thin out to a much lesser density. So unlike, say, the ocean that has a nice, well-defined top to it, right? You've got water and it sits there in the ocean basin, and then there's a clear top where the ocean stops. The atmosphere just kind of slowly fades out as it goes away from the Earth. So there's no, clear hard limit to where the top of the atmosphere is. It just sort of fades out until we're effectively in the vacuum of space. So when we look at the atmosphere, the densest layer, the layer closest to the Earth's surface, is called the troposphere. And the troposphere actually contains about 3/4 of all the air on the Earth. So it's just that much denser than the layers above it. And we all live in the troposphere. The air around you is the troposphere, and that's true for pretty much your entire life. It's pretty rare that people actually leave the troposphere going upward. I mean, I guess we get out of the troposphere if you go in a submersible under the ocean, but going upward, we very rarely get above the troposphere, because the troposphere goes up about 10 kilometers. And as you can see on the diagram, a commercial jet, if you were to fly to California or something, you'd be going maybe at the top of the troposphere. Most of our clouds are located in the troposphere. And our highest mountains on Earth, the peaks of them are still within the troposphere. So you see Mount Everest there doesn't stick up out of the troposphere. And as you go up in the troposphere, it does get thinner in the air. So back in 2019, I co-led a trip with 5 SRU students to China, and one of the things we did while we were down there was we went to a place called Jade Dragon Snow Mountain, which is a mountain that the top of it is nearly 7 kilometers above sea level. So not quite the height of Mount Everest, but way up there, certainly way higher than any mountains you'd find in Pennsylvania. And when we went up to the top of that mountain, we actually had to carry with us oxygen canisters, and we would have to take little puffs from the oxygen canisters as we walked around, because the air was so thin it was hard to catch your breath and get enough oxygen up there, but we were still within the troposphere. The other thing about going up Jade Dragon Snow Mountain is, as the name suggests, there's snow up there, even though it's fairly close to the equator. This is in southern China. And that's because in the troposphere, the higher you go, generally speaking, the colder it gets. And that's probably something that you've noticed even just here in Pennsylvania. You can often tell the difference in temperature between being on top of our, by world standards, little mountains versus down in the valley. And sometimes you'll see that there's snow on top of the mountains, but it's warm enough that it has melted in the valleys. And that's characteristic of the troposphere, that it tends to get colder as you go up within the troposphere. And that's illustrated by the red line there. That's a temperature graph. Above the troposphere, we have the stratosphere. And the stratosphere is notable for two things. One, that temperature relationship changes. So it actually gets warmer the higher you go up in the stratosphere. The other important thing about the stratosphere is that's where the ozone layer is located. So there is this section in the middle of the stratosphere, you can see it on the diagram there, that has a really high concentration of ozone. So ozone is just molecules of oxygen made out of 3 oxygen atoms. Standard oxygen, what you're breathing all the time, is O2, 2 atoms of oxygen together into a molecule. Ozone is O3. You got 3 molecules of oxygen, and the ozone layer plays a really important role in protecting us from ultraviolet radiation from the sun. It blocks a lot of that UV radiation, and that's located in that stratosphere. If you keep going up above the stratosphere, you get up above about 50 kilometers, and we get to the mesosphere, where the temperature relationship changes direction again and starts getting colder as you go up through the mesosphere. Then you get 85 kilometers or so up and you enter the thermosphere, the outermost and least dense layer of our atmosphere. So we've got these 4 main layers to the atmosphere. The key things to keep in mind are that we live in the troposphere. Almost everything important about our weather is happening in the troposphere, but then the ozone layer is in the stratosphere. So this diagram shows what our air down here in the troposphere is made out of. So this is sort of average, clean and dry air. So this is air that doesn't have like extra stuff in it from smoke or, car emissions or something, and it's dry air, 0% humidity, because our air can have wildly varying amounts of water vapor in it, and that's something we'll talk about later about, what happens when air has more or less water vapor in it. But this is just if the air is dry, so 0 water vapor, what else is it made out of? And you'll see that our air, the air that you're breathing right now, is about 78% nitrogen. So that's the main thing that our air is made out of, is nitrogen, N2, 2 atoms of nitrogen stuck together into a molecule. Then the number 2 thing that it's made out of is oxygen. It's about 21% oxygen. So there's a lot of oxygen in our atmosphere. And that oxygen is actually really important for the existence of fire on the Earth, because for fire to burn, it needs to take in oxygen. Fire is a chemical reaction that absorbs oxygen from the air to make it go. And if that oxygen percentage were to drop down more towards like 15% oxygen, it would become really difficult to keep a fire going. That fire wouldn't be able to get enough oxygen to continue burning unless you were artificially adding extra oxygen into it. Just the general air wouldn't be enough. On the other hand, if you bumped that percentage up, if you got up to like 30% oxygen, it would be incredibly difficult to stop a fire from burning. Most of our methods for putting out a fire involve depriving it of oxygen. So if you imagine one of those little bell-shaped candle snuffers, right, what that's doing is it's preventing oxygen from getting to the candle, and so it goes out. You spray, firefighting foam on a fire, that is depriving it of oxygen. But if our air was more like 30% oxygen, it would be incredibly difficult even to put a fire out. So the balance of the amount of oxygen on the Earth makes our planet a great planet for fires to be able to happen without just like burning the entire planet down. So we've got our nitrogen and oxygen that together comprise about 99% of our air, just those 2 things. And then you can see a little sliver of almost another percent being argon. And so that's an inert gas, just single molecules of argon, or single atoms of argon hanging around. And that leaves only the tiniest little sliver, so small that you can't even really see it on this large pie chart, of all of the other things that make up our air. So our air has little amounts of things like xenon, neon, hydrogen, helium, krypton, and very important for this class, carbon dioxide. So you'll remember the atmosphere is one of our major stocks of carbon. In our carbon cycle, right, one of the main places that we find carbon, and an essential one that's constantly receiving more carbon, inflows of carbon and having outflows of carbon to other places, is the atmosphere. And all that carbon in the atmosphere actually only makes up about 0.038% of our air. So the amount of carbon dioxide that's in the air is in some sense, really, really tiny, certainly compared to oxygen. On the other hand, because that carbon dioxide is so small as a percentage, that means human activity can very easily throw it out of whack. So things that people do can't really make an appreciable difference in the amount of oxygen in our atmosphere. Right? We can't really add or subtract enough oxygen from the atmosphere to really change that percentage in an appreciable way. On the other hand, carbon dioxide is small enough to begin with that human activity can easily increase it percentage-wise. We can double the amount of carbon dioxide in our atmosphere, and we're well on our way to doing that. And in fact, that number that you see on that slide there is actually an outdated number. This diagram is a few years old. I've just been, reusing it every time I update the PowerPoint. And so in 2023, when I'm making this video, the percentage of carbon dioxide in our atmosphere is actually more like 0.042%. So even just in the few years since this diagram was made, that percentage has gone up. And if we were to go back in time to before the Industrial Revolution, so before we started burning fossil fuels in large quantities, that percentage carbon dioxide would have been about 0.027%. So we've already added quite a bit of carbon dioxide to the atmosphere, and we're continuing to add more. So that's the piece of the atmosphere that we're going to spend a lot of time talking about because it's so crucial for our climate. So here's an illustration of one of the most famous diagrams in climate science called the Keeling curve. So it's named after a guy called Charles Keeling, who began recording CO2 levels at Mauna Loa, Hawaii in the 1950s. So he was at the observatory there, and he started to measure the amount of CO2 in the atmosphere. And Mauna Loa is a great place to measure that because the air up there is really nice and clean. So you're in Hawaii, you're far away from any like industrial centers that might be putting extra stuff into the atmosphere, etc. So you can get a nice good read on the typical amount of various gases that are making up the atmosphere at a location like Mauna Loa. And so what you see in the diagram there, the red line that zigzags up and down is based on monthly observations of atmospheric CO2. And the black line that runs through the middle is smoothed out sort of yearly average. So you'll notice two key things here. One is that red line has this annual up and down cycle, right? It's a very regular zigzag kind of cycle. And that's due to the cycle of growth and dormancy of plants. So if you remember back to our discussion of the carbon cycle, right, one of the big inflows and outflows to the atmospheric stock is carbon being taken up by plants during photosynthesis and then getting released back into the atmosphere by respiration from animals that ate those plants. So whenever plants are growing, they're taking carbon out of the atmosphere. And then if those plants stop growing, so if, for example, it's the winter and those plants are dormant, they're not growing, they're not photosynthesizing, or at least not photosynthesizing as much as they did in the summer, then animals are still going to be eating and breathing out CO2, and so the CO2 level is going to come back up, and then spring comes, plants start growing, and the CO2 levels get drawn back down because those plants are taking up more CO2. So you have this annual cycle that during the summer, the CO2 levels come down because plants are growing more. During the winter, the CO2 levels go back up. And now you may be saying, but wait a minute, when it's summer in the northern hemisphere, it's winter in the southern hemisphere and vice versa. So shouldn't those cancel out, right? When plants are growing at their greatest in the northern hemisphere, they're dormant in the south, and when they go dormant in the northern hemisphere, they're growing at their greatest in the south. And that's true. There's that reversed annual cycle between the northern and southern hemispheres. However, there are just a lot more plants in the northern hemisphere because the northern hemisphere has a lot more land than the southern hemisphere. The southern hemisphere has large areas of ocean that don't have a lot of plant life going on. in them. And so the northern hemisphere's seasonal cycle tends to have a bigger impact on the global amount of CO2 than the southern hemisphere's. The southern hemisphere offsets it a little bit, but the northern hemisphere is dominant, and it gives us that annual up and down jaggedy motion that we see in the red line here. But then from both the red monthly line and the smoothed out annual averages in the black line, we see a clear upward trajectory in that line. All right, so when Keeling started making his observations, you can see that CO2 in the atmosphere was down around looks like about 315 parts per million. Now, a part per million is just another way of writing a percentage. You're just moving the decimal point over 4 spots, right? Because a percent per 100. And to avoid having decimal points and a bunch of zeros in front of everything, when we talk about CO2, we often put it in terms of parts per million, right? So a 300 parts per million is equivalent to 0.03%. Right? You can just convert it back and forth, shift the decimal place 4 places. So when Keeling started, as I said, looks like it was about 315-ish parts per million CO2. That's already above what we know to be the pre-industrial amount of CO2 in our atmosphere. But then since the 1950s, as we've continued to collect this data, you can see it has steadily gone up until now we are closing in on 420 parts per million. So officially in 2022, the yearly average was 417 parts per million. So we're continuing to go up at this fairly steady trajectory that we can see in the Keeling curve here. So the Keeling curve is our direct observations of composition of the atmosphere, right? When we've been directly measuring the atmosphere at the time that we're getting this data from. But we can actually trace the composition of our atmosphere farther back in time. And we call this the study of paleoclimate, so ancient climates. And we can study both the temperatures that the world was experiencing and the composition of the atmosphere in the past. And we find that our CO2 levels go up and down with the temperatures of our Earth. So we can see changes in the CO2 levels that follow these cycles of glacial and interglacial periods that last about 100,000 years. So on the diagram there, the blue line is a reconstructed atmospheric carbon dioxide going back several 100,000 years. And you can see this cycle of going up and down, up and down. So where it's up, where we have higher CO2 levels, those are our interglacial periods. So the comparatively warm periods where the ice sheets have retreated. And then you see the CO2 levels dropping and getting down to a low point. That is our glacial periods, when the Earth was cooler and you had giant ice sheets spreading out from the polar regions. And what we call the last glacial maximum. So the last time that most recent glacial period was at its peak was about 18,000 years ago. And at that point, the glaciers actually reached Slippery Rock. So the town of Slippery Rock is right at the edge of where the glaciers got to during this last glacial maximum, which I think is a cool thing about Slippery Rock, that we're right at the edge of where the glaciers were. So that was that coolest point in recent history. And then since then, you can see the blue line going back up. We had increasing carbon dioxide and increasing temperatures as we came out of that glacial period and got back to about where the CO2 concentrations were at those previous interglacials. You'll see the previous interglacials, we had CO2 concentrations somewhere between 275 and 300 parts per million. But then over the last 100 or so years, which is a time period so small, you can barely see it, barely takes up any side-to-side room on this graph, we have driven our CO2 concentrations even higher than that. So the red section at the end of that graph that leads up to where it says current level, which again, this diagram is a little out of date because now we're up above 400 parts per million in 2023. But that current line, you can see it shooting way up above where we were during both this most recent interglacial period that we started from and any of those past interglacial periods. And just to give you a sense of the time scale that we're talking about here, that last glacial maximum was 18,000 years ago. Written history doesn't begin until about 5,500 years ago. That's some of our earliest actual written records of human history. So we're dealing with some pretty big time scales here. But the key thing to note here is that our current CO2 levels are way above normal for any of these past interglacial periods. We are way outside of what our Earth has experienced in this period that we're able to reconstruct. So you might be asking, how do we reconstruct this? Right? If we didn't have Charles Keeling out there taking air samples 400,000 years ago, how do we know what the atmosphere was made of? And we do this through ice core records. So when you have a glacier that is forming, it's going to form in layers. So each year's snowfall is going to fall on that glacier, and then it's going to get compressed under the next year's snowfall and the next year's snowfall. So each year is going to give you a little layer of snow that, as the weight of other snow on top of it pushes it down, it gets compressed and frozen into a layer of ice. So inside of our glaciers, we have these annual layers of ice. They're almost like tree rings. Right? You get a layer of ice for each year. And when these layers form, they trap little bubbles of air, right? If you've got snow laying on the ground, right, that snow's got a lot of air in it, and then you compress that snow and freeze it into ice, you're going to trap all that air in there. So all these tiny little bubbles of air in this ice. So it's like having a whole bunch of air samples from the past that are sealed away in this ice. And so then we can drill into the glacier and remove this cylinder of ice that we call an ice core. And the pictures there kind of show you a bit of the process that we drill down and remove this cylindrical piece of ice. And then we can take that ice core and we can take samples out of it. And we can, count the layers to figure out what time period we're in, take a sample, pull the air out of those tiny little bubbles, test it, see what CO2 concentration and other things are in it. And we've done this in our two major ice sheets that exist on the Earth, in Greenland and in Antarctica. And between those, we've been able to compile that paleoclimate record that we were looking at on the previous slide. So we were talking about how our CO2 concentrations right now are way out of the range of what the Earth has experienced in the past. And this is part of what underlies the concept of the Anthropocene. So this is an idea that Earth scientists talk about, that we are in a new geological time period that is characterized by humans as a dominant force shaping the Earth. So human activity making a major impact on how our Earth systems work. That is a thing that distinguishes the current moment from anything the Earth has experienced in the past. And so we label our current time period the Anthropocene, from anthropos, the Greek word for human. And this Anthropocene concept is controversial. There are a lot of debates about it. So one debate is, when did the Anthropocene start? When do we put the starting date for this geological time period? And there's a bunch of different places that we might choose to put this starting point in terms of moments at which we had a shift or an increase in the amount of human impact on our Earth system. So I've got some of those key dates listed there on the slide. So we could go back to something around 150,000 BCE is when Homo sapiens evolved, right? That's when our species first came about. So obviously the Anthropocene can't start before that, because there wouldn't have been our species, though there would have been other, our ancestral species, Homo erectus and stuff before that. But if we're going to be talking about Homo sapiens, we've got a point that we can't go back past. Then as we move forward, one of the first major potential human impacts on the Earth system that we can point to is the extinction of megafauna in various places. So the timing of those extinctions vary. Some of them are as far back as 60,000 years ago, some closer to 10,000, where a variety of very large animals in certain continents got or went extinct. So in Australia, there used to be gigantic kangaroos, wombats the size of a bus, and these kind of like gigantic animals that have gone extinct. Here in North America, we had giant ground sloths and woolly mammoths and various other large creatures that have gone extinct. And there's a lot of debate among archaeologists about the degree to which humans were responsible for the extinctions of those megafauna. And, were humans more responsible in some parts of the world than others, etc. But that's sort of the first thing that people have pointed to as potential major human impacts on the Earth system. We come up to about 8,000 BCE, so about 10,000 years ago, we have the first farming. So farming dramatically increases the amount by which humans are changing the ecology around them. Right, we're now clearing out all of the plants that had grown there on their own and deliberately putting down seeds of whatever we want to grow and harvesting it and weeding it and all this kind of stuff. It has a much bigger amount of impact on the ecosystems around us. The earliest farming started, again, about 10,000 years ago, or about 8,000 BCE. So that was an important step forward or an increase in human impact on the Earth system. We get up to about 1 CE, so about 2,000 years ago. And that's where we can start to actually detect pollution from human activities that is going beyond the local area. So, human activity has always had the potential to pollute the immediate area around where people were living. But starting about 2,000 years ago, we can actually find pollution generated on one continent in geological records on another. So if we look at those ice cores from Greenland, we can actually find lead that was put into the atmosphere by lead smelting being done in the Roman Empire. So Roman Empire over in the Mediterranean was putting so much pollution into the air by making lead and other metals that they were smelting that it was actually visible in the records in the Greenland ice sheet. So there we're starting to see a global impact of human activity. Another key point was about the year 1500, where we see a massive population crash and resulting land use change in the Americas as a result of the beginnings of European colonization. So as Europeans started to cross the Atlantic and come into contact with indigenous people in the Americas, you had massive numbers of people dying from diseases introduced by Europeans, as well as being forced off their lands by conquests, and so forth. So you lost tons and tons of people in the Americas, and with the loss of those people, those indigenous societies weren't able to keep up their farming practices. And so you had big ecological shifts and included massive regrowth of forests in places like the Amazon. And this had global impacts on climate. If you've now got this big change in the ecology of these two continents. So the start of European colonialism in the Americas is another key point, a key inflection point in the amount of impact that people are having on the world. Another key point is around the year 1800, where we have the beginnings of the Industrial Revolution. So here we have found new ways to mass produce goods, which hugely increases our demand on resources and in particular increases our demand for fossil fuels. So first coal, then later oil and natural gas we start using in vast quantities, much more than anybody had in the past because we're fueling our industrial activities, our factories, our motor vehicles, etc. Really start to take off after about 1800. So that's another key inflection point. And then the most recent point that gets pointed to as a start date for the Anthropocene is about 1950, where we have what's called the Great Acceleration, where as the world was coming out of World War II and reconstructing, we saw that had this economic boom and a massive increase in our production and use of a variety of sorts of materials that had big impacts on our Earth systems. So we started using artificial fertilizers on a huge scale, and those impact the atmosphere and the water and the land. We started industrial processes that created new kinds of chemicals, plastics and so forth, and that put out enormous amounts of pollution on a much larger scale than we had before. We see big increases in the use of those fossil fuels, really kicked up after 1950. So at that point, we have this vastly increased amount of human impact on the operation of our Earth's systems. So that's one controversy, is when did the Anthropocene start? Another controversy is that name Anthropocene. That's the era of humans, because that name seems to just blame humans in general, right? It's our species that's at fault, or that's our species that's causing these changes. But it's not just our species, all of us in the same way. These changes are the result of particular social systems that we are engaged in. And some people's activity is contributing to these changes more so than others. So you'll see proposals that instead of talking about the Anthropocene, we should be talking about, say, the Capitalocene. Right? This is the era of capitalism. It's the capitalist system, not just humans as a species, that is causing these changes. Or the plantation scene, because the idea there is that plantation-style resource extraction was the key thing that increased this human impact on the Earth. You'll also sometimes see the term Cthulhu-scene, named after the mind-destroying elder god from H.P. Lovecraft, Cthulhu, based on the idea that people have made things weird, that we have just upset all of the balance and the ability to figure out what to expect from our environment. So, we're kind of being like Cthulhu in what we're doing to our environment. So, where do we place the responsibility for this? Should it be on all humans as a species, or should it be on particular social systems? This is another controversial aspect of this term Anthropocene. And it's important to keep in mind this question of who's responsible for these changes and who benefits from these changes versus who is experiencing harm from these changes, because that's very important to understanding what we can do if we want to change what's happening. And so as one illustration to this, since we've been talking about carbon in the atmosphere, this is a graph of annual total CO2 emissions broken up by different regions and countries in the world. So you can see overall, the shape similar to that Keeling curve, but extended backwards in time, that our total emissions worldwide of CO2 were so small you could barely even see it on the graph there back into the 1700s, 1800s. So starts growing by the late 1800s, and you can see on this graph that great acceleration. 1950, the angle of that top line, the total CO2 emissions, kicks way up, goes up at a much faster rate after 1950. But then if you look at how it's broken down, right, each colored stripe there is the emissions from a particular part of the world. You see some parts of the world are contributing a lot, others much less. So you see Europe making a very big contribution, but declining somewhat over the last 50 years or so. The United States being a very major contributor throughout this period, and then the rest of North America, so we're talking about like Canada and Mexico, right? Only the very thin little light green stripe there. South America, very little contributions throughout. Africa, the entire continent of Africa, making only a very small contribution to total CO2 emissions. India, you can see there, was making only a very small contribution until very recently. And you see the size of the yellow stripe for India growing a whole lot over the last few decades. Likewise with China. China was a very tiny little stripe there for most of it, and then has grown hugely since then. Similar for the part that's the rest of Asia. So not all people, not all regions of the world are contributing equally to this increase in carbon dioxide in our atmosphere. So that's what I wanted to say about the composition of the atmosphere for this week. And since this is our first lesson and you've got your exam this week, there's no lab assignment, no activity for you to complete this week. So just this information will be on your final test at the end of our course. So I will see you next week.